Okay, we are looking at a base pair. These are acids and bases equilibrium, and we really haven't talked about the bases at all. So this part is on bases. They're very similar to figuring out acids. We are not doing the old-fashioned definition of a base, something that gives a hydroxide, but something that is a proton acceptor. So this base is a proton acceptor. So is that base. And water in this case will act as the acid and be a proton donor. So you can see the way that this is set out. To express this as Kb is as follows. You can probably see that the product's over the reactant. That seems pretty obvious. Let's go straight to an example. Just a reminder, a weak acid will have a strong conjugate base. And on the flip side of that, obviously, a weak base will have a strong conjugate acid. Just a reminder, I know you already knew that. Okay, here's the example. We are looking at 15.0 molar ammonia, which is a base because it is a proton acceptor. There's the Kb. You have to find pH. So again, I'm going to condense it, but you should be able to follow along now fairly easily. We've done so many. Step 1, major species. And it is NH3 with a Kb and H2O with Kw. Those are numbers you already know. Taking a look at this, we can then identify that NH3 is larger, the Kb is larger than that of water. So we can write the expression is as follows. Please note you should have been able to write the equation for this. There it is, products over reactants. The next step is you should create that table. I didn't say I was going to create it, with the initial concentration and equilibrium concentration, so pause and do that. Otherwise, you might be smart enough to just continue at this point. You need to solve for X, which of course will be the concentration of OH negative today. And here it is. It's 1.6 times 10 to the negative 2 molarity, which is the concentration of hydroxide ion. Now, we need to find pH. If you remember, Kw is equal concentration of hydrogen ion times concentration of hydroxide ion. In this particular case, we know Kw, and we know the concentration of the hydroxide. So you can plug this in to find the concentration of hydrogen ions. Do that. Here is the answer, 6.3 times 10 to the negative 13th molarity of hydrogen ion. You might want to validate that. And now solving for pH. Should be able to do that easily. And this came out to be 12.2. Good. So you just have to take that into account, that Kw stuff. And let's do another example, one that's not quite so obvious. This is NaF, and there is the Ka. You need to find the pH of this. Again, identify the major species. Remember to always look at salts, that's a metal with a nonmetal, as weak acids. So NaF you will consider to be like a weak acid. The major species here is Na+, F negative, and H2O, because that comes apart fairly well in water. Since HF is a weak acid, however, it dissociates poorly, F negative must be a strong base, right? Those are those conjugates. That means it holds on to hydrogen ions. So when you put NaF in water, they come apart. And the equation that you're looking at is F negative plus H2O at equilibrium with HF and OH negative. It will yank that hydrogen off the water. So to express Kb, we will have this. Always write the expression. Now, if you recall, remember that for a weak acid and conjugate base, Kw equals Ka times Kb. That's handy to know, because you should be able to figure out Kb. I gave you Ka, you know Kw, and here is Kb. There it is, 1.4 times 10 to the negative 11th. So now you have Kb. For this expression, you have that number. Now, I'm showing you how we walk through this again. It's just a little reminder, initial and at equilibrium concentrations. Might want to take a look at it. Just a reminder. Solving for X, 2.0 times 10 to the negative 6th molarity, X. And that will be the molarity of what? Of the hydroxide ion. If you know that, then you know POH. So POH is equal to 5.69. You can easily solve for pH. You can always do 14 minus POH equals pH. Oh, there's fireworks. How exciting. This is end of part 9.